Okay, this particular question we have over here, we have a compound system. We have a push bike where we have a pedal pushing down at 450 newtons. We have a gear that the pedal is connected to, which contains 50 teeth. We have 20 teeth on the gear connected to the rear tire. We have an outer diameter of 700, let's assume it's in millimeters because by default it looks like it's going to be in millimeters. And that's in diameter. And then we have a force down here of 75. Hold up. So now before we start this question, we need to find the velocity ratio, and this over here is just a multiple choice question from a HSC exam, but we're going to find more information from it. Before we start, let's look at the HSC exam. This is the formula sheet. So this is the information that you'll be given in any style of Stage 6 exam. We're going to look at the areas regarding machines. Over here we have MA. So I'm just going to write these formulas down over here so we don't have to refer to them again. MA equals L over E, which stands for mechanical advantage equals load over efforts. And then we have velocity ratio, VR, equals distance that the effort has moved over distance that the load has moved. And then the last one we have here is this funny looking N, which stands for efficiency, equals mechanical advantage over velocity ratio. These are our three key questions. The other things we have, if we look at gears, we can over here we find velocity ratio of gears is the number of teeth. Velocity ratio, let's just call it G, equals the number of teeth on the driven gear. So driven teeth over driver teeth. Okay, so let's go back to our question over here. The first thing we're going to find is our velocity ratio. So when we have a system of compound gears, we could already find a formula of the velocity ratio of a single gear because we have dE over dL. When we have a compound system of gears, right? So let's this isn't a compound system of gears. This is just a compound system. Let's say over here, I'm just going to draw this out again. We have this, and then we have our larger wheel over here, and this over here is diameter of 700. This over here is 20T. This over here is 50T. This over here is 170 millimeters. We also have our forces going here of 450. And this over here is a force of 70. So we actually have two machines in this system. Right, the first one that you can see is the pulley. Well, it's a hybrid between a pulley and a gear, but these are like gears, right? Because there's a 50-tooth gear over here and a 20-tooth gear over here, but they're just connected by a chain. But they're still going to act as gears, except their direction is not going to change. So that's one system, is the gear. The other system is weird in this sense because it's actually split, right? The other system we have is between this, where the pedal is, and the connection to the road. Right? This over here is, if we were to remove the gear, we would get a scenario where, so let me just draw those two systems. We have one system over here, which is our 50-20 system. The other system actually looks like this, where we have this big wheel over here that is the 700 millimeter diameter wheel, but then we also have a single pedal. So think of it like like a unicycle. Right, so this is the other system that we have here. So we have like a pedal and a wheel. And if we want to even simplify this even more, we can go to saying, well, this is the same as having a pedal over here, and if the wheel is just touching the ground in one location, right, then this over here is going to be 700 divided by 2, because that would just be a radius, and this over here is still 170, and then we can simplify that even more by saying, well, if we still have the pedal over here, and that's 170, and this over here is going to be 350, which is half of 700. And then we have this over here, we said was going to be 450 newtons, and this over here, if that's 70, this over here clearly looks like a lever, right? Looks like a first order lever, I think. So this is clearly a lever. And this is clearly a gear system. So when we want to find our velocity ratios, we just times, so we find the velocity ratio total equals the velocity ratio of the first machine times the velocity ratio of the second machine, and so forth if you had 3, 4, whatever amount of machines. So we just times in the velocity ratios of the individual machines. If we get to the velocity ratio of the, let's call this machine number 1, and we'll call this machine number 2. If we find the velocity ratio of the first machine, we need to get the when we have to define which is the driver and which is the driven gear. So how we do that is we look at our system from the very start, which is where you're putting your feet on the pedal, and it ends at where the wheel is touching the ground. So you got to think of where your individual component lies in there, and then is that component where the input and output of each machine is in the larger system, and then is that input or output of that device, is it going to be closer to the input, like in this case where the pedal is, or is it going to be closer to the wheel? So maybe I explained that one a bit weird, but so if we have our gear over here, we can clearly see that this gear relates to this part up here, and this gear, this part of the gear, the 50 tooth, is, if we see how force is traveling through the system, we have to first enter through this pedal, and then we're entering into this gear. But then this gear is then transferring its energy over to the 20 tooth gear. So for this particular system, this 50 tooth gear is transferring its energy over to the 20 tooth gear. So in this particular geared system, this one is driving gear 20, the smaller gear. So in this particular case, this one is going to be the driver, and this one is going to be the driven. The dr, and this is going to be the dn. When we look at this larger example we have over here, this lever over here, we can find out which one is the E and DL, or we can just define it as E and L for effort and load. Effort is going to be where you're putting your pedal in, so everything on the pedal side is going to be our efforts, and everything on where our 70 Newton is, or where the tire touches the ground, that's going to be our loads. That means we can start to write out our formulas here. So now we can start writing out our formulas. We know that our first one we have is our gears, so it's going to be driven over driver. And then for our second one, we just have to write our distance our effort moves over our distance our load moves. And then if we figure out this formula, we should have our driven is going to be 20 teeth over our driver is going to be 50 teeth times the distance our effort moves is, well, it's going to move in a circumference around a pulley, but we're going to get to the point where we get to eliminate our pi and our angle to find our rad. So we just only care about the radiuses. So we're going to get to 170 over 350, and let's plug that into the calculator and see if that is correct. So we're going to get 20 over 50 times 170 over 350. Gives us an angle of, gives us an answer of 0.194. 0.194. Alright, so the next part of the question, this is not part of the multiple choice question, but this is extra engineering questions. We want to find the efficiency of this particular system. Alright, so we're going to be finding the efficiency of this system. Now, if we look over here in our formulas, we have our efficiency equals mechanical advantage over VR. We already know what our VR is because we've answered it over here, 0.194, and we know so we have to find the mechanical advantage. So if we want to find the mechanical advantage, we're going to go MA equals load over effort. So we are lucky in this particular scenario that they've given us the load and the effort. They've given us 450 over here and 70. Oh, sorry, wrong one. 450 over here and 70 newtons over here. So where we're putting our pedal in is our efforts. So that's going to equal 450. And then our load is going to be our 70 over here. If we type it into the calculator, I've prepared this one earlier. Never mind, it's gone. If we put in 70 over 450, we get an answer of 1.5 recurring. So let's just round that. Let's just do it to let's do 3 decimal places because we did 1.94. Why not? So 0.156 is our mechanical advantage we have there. So now we can find our efficiency because our efficiency is going to equal MA over VR. So that's going to equal 0.156 over 0.194, and this should equal 0.156 over 0.194. That should give us an efficiency of 0.84, which is the same as 80.4%. Either one of those will be the right answer when it comes down to the efficiency. So now the last thing we have here is we're trying to build a scenario question. We're going to say, how fast do you need to pedal in RPM, so the pedal over here, how fast do you have to pedal in RPM to move at a speed of 25 kilometers per hour? So we have this question over here where we have a velocity. We say, we know our velocity, this question we want is 25 kilometers per hour. Our velocity, so we know that we're moving, if we look at this part down here, we are moving this ground is going to be moving at 25 kilometers an hour, which means so as this is moving, if we move a whole circumference, worth of distance, we have rotated the wheel once, the rear wheel. So we can work our way to a formula here where we can find that our velocity is going to equal our circumference, which let's just write C now for circumference. That's not the speed of light. I'm just going to say, in fact, just to make sure we're not consuming at the speed of light, we'll put it inside the brackets. So whatever our circumference of our wheel is, times its RPM, well, RPM is going to be revolving in in minutes. So it'd be like revolutions per sec. I'm just going to write revolutions. So if we look at our circumference times our revolutions per whatever our, let's just say seconds, that's going to give us an answer for how fast we're moving in meters per second. Right, same over here is if we do revolutions per hour or whatever, but the point is we are going to be using our circumference. One whole circumference will move our wheel forwards one whole. If we rotate our wheel once, we're going to move forwards one circumference. So we can find out by this how many revolutions the rear wheel has to do to move. Once we find out how many revolutions the rear wheel has, we can use our velocity ratio, where our VR equals the distance our load moves versus the distance our effort moves, to find out how many revolutions our pedal has to do. So let's break these down. So I want my answer to be in, well, we want our answer to be in RPMs. So if we actually change this, we want to actually make our answer, we want our circumference times RPM, which means we have 25 kilometers per hour. We have to change that into meters per minute. So this is a blasphemy amount of engineering transformations we do here. So we're going to get 25 kilometers per hour. For it to go to meters per second, meters per minute, we have to times it by 25 times 1,000 to get to meters, and then we're going to divide it by 60 equals 25 times 1,000 divided by 60. This should give us 416.7 meters per minute. That is the most disgusting unit I've seen ever. Meters, so 416 meters per minute. Then we can plug this into. We can then plug this into our equation up here. We're going to get 416.7 equals our circumference, which what is our circumference? Our circumference is it's just 2 pi r, right? Or diameter times pi. So we have 416 for our velocity. Then we have our circumference, which is just going to be 700. Point, because we have to put in meters. So 0.700 times pi times RPM. So our RPM is going to equal it's a fraction, 416.7 divided by 0.7 times pi. Our RPM should be 189 let's just round that off to 5. So that's our RPM. Then I'm going to try to fix this all into one page, so it's going to be easier for you to read. And then over here, to finish us off, we are going to we're going to use our velocity ratio equals dE over dL. We know that our velocity ratio is 0.194. Now when we're doing distance, we can do RPM as a distance because that's revolutions. Then because we'll just do it like per minute. Our dE, we don't know what our dE is because we want to find what our dE is, but we know what our dL is. We know that our dL is 189.5. So then that should get us to dE equals we should have that times 0.194. So then we should get 36.8 RPM. Sorry, I did that one all down there at the bottom. But so we have VR equals dE over dL. We know what our VR is. It's 0.194. We know that our dL is 189.5. That's the amount of revolutions that it has to do. And then we just rearrange that formula to get dE. So we're going to get 0.194 times 189.5 equals 36.8 RPM. So that's how you get that answer for finding out the RPM required to move at 25 kilometers per hour. And just as a bit of understanding, does this make sense if you're riding a push bike? Our push bikes are designed so your legs move slower than the speed that you're moving. You're putting in more force. So if we look at our actual original setup, over here we're putting in 450 newtons of force and we're only getting out 70. So we're getting less force out. So it should make sense that if we're losing in force, we should be gaining in something else. And we're gaining in the rotational speed. We only are putting in a rotational speed of 36.8, but we're getting out a rotational speed of 189, which is why bikes are not so much an efficient, but a very effective way to convert, because our human muscles can produce more force than their speed, which is why then bikes get that higher, allow you to utilize that. And so that's this style of question.